Hello and welcome to this webinar broadcast. It is the first broadcast in our series, Weathering Change, Local Solutions for Strong Communities. This is the 6th year of the series, and we're happy to welcome you to this first broadcast. Next slide, please. I'm Abigail Abrash-Walton. I serve as co-director of the Center for Climate Preparedness and Community Resilience at Antioch University, New England. I also direct the master's programs here in the Department of Environmental Studies. And it's a pleasure to have you all joining us for this kickoff. The goal of the center, our mission, is to strengthen communities to prepare, respond, and recover in the face of climate impacts and other disruptions through collaborative innovative solutions. And you see there the link on the screen for the website, and it's also in the sidebar chat function. So if you want to click through and get a sense of our programming, you certainly can do that by clicking on that link. Next slide, please. One of the things that we have recently begun is a certificate program in climate resilience. This is designed for working professionals. It's a 9-credit certificate, but you can individually take the courses that are 4 weeks in length each. Those do carry 1 graduate credit apiece. You can audit those courses, and it's an excellent way to network across the country and also into other countries as well. We've had some participants from Canada as well in this certificate program. It's a great way to build your network and to build your capacity to do climate resilience work in the communities in which you're serving. So you see a link there, and there also is a link over there in the chat box where you can get some more information. I do want to let you know that the next course is on climate change, the science, uncertainty, and risk. This is an online course that begins September 8th this year. Co-director of the center and professor here at Antioch, New England, Michael Simpson, is the instructor for that. So this is a great opportunity to focus on the science of climate change and just to become fluent in understanding risk and uncertainty when it comes to a changing climate. Next slide. So it has been a pleasure, NOAA's U.S. Climate Resilience Toolkit team, in presenting this webinar series. And I want to thank Ned Gardner, the engagement manager for the toolkit, for moderating today's session. And I now am happy, Ned, to turn the mic over to you and to sit back and enjoy the broadcast. Thanks.
Okay, thanks, Abby. And good afternoon, everybody. Thank you all for joining. And the U.S. Climate Resilience Toolkit is a website that brings climate science, the subject of today's webinar, together with tools, data, assessments, and expertise that people need in order to undergo adaptation processes. We have a resilience framework, the steps to resilience, that incorporates risk management with decision making. And so if you have not checked out our website, there's our URL. We welcome all feedback. Feel free to use the online form to reach out to us if you have any questions about the toolkit. Climate science in and of itself can't solve all society's problems. We all have to roll up our sleeves and make use of scientific information when and where we can. And so today's speaker is someone who embraces all aspects of the science and also how to help people become better citizens. Erich Osterberg is our speaker today, and he's going to be speaking about climate change, what's natural, what's human caused, and how do we know. His own personal website is very short and sweet in describing his personal mission to explore the signature and causes of climate change, determine how fast glaciers respond to warming, assess long-term air pollution trends and sources, and train the next generation of polar scientists. So with that, we're going to make a transition back to Erich. I have put a few logistics up on screen while we're making the transition. Please note of these. If you have any questions, use the chat box to get some help from any one of us who's online to help you. I'm going to transfer control of the screen over to you, Eric. If you would like to share your screen, we will take it from there.
All right, now can you see that, Ned?
Yes.
You seeing my screen?
Yes,
excellent.
I can see and hear you very clearly. Thank you.
All right, wonderful. Well, thank you, Ned, for the introduction and for the invitation to be here. And thanks also to Abby and to Michael Simpson at Antioch, who invited me to give you this webinar today. So as Ned just said, we're going to talk about climate change and try and tease apart here what is natural, what is human caused, and how is it that we know this. And so to begin, I just want to make sure that I acknowledge a bunch of people. All of the research that I do is highly collaborative. There's a whole team of people here at Dartmouth, including other faculty like Bob and Meredith and John Winter and Justin Mencken, and then a bunch of graduate students and my laboratory managers. And then we use a lot of undergraduates to do really outstanding research here in the laboratory. And some of them are even writing publications as first authors by the time they're seniors. And then collaborators at UMaine, UNH, Cameron Wake may be known to many of you here in the Northeast. And then our funding generally comes from the National Science Foundation. They've been very generous in funding us over the years. And then a lot of what we'll talk about today is ice core research. And so the National Ice Core Lab out in Denver, Colorado, has given us a lot of logistical support, as well as CH2M Hill Polar Services, who helps us plan these expeditions, and the 109th Airlift Wing of the Air National Guard, which is out of upstate New York. They're the ones who actually fly us onto these ice sheets, which is pretty remarkable. All right, so I want to begin with this figure of global surface average temperature, which most of you are probably familiar with. This is on the left going back to 1880, and on the right is today. And what we can see here is that the Earth has warmed by about 2 degrees Celsius, Fahrenheit, sorry, since 1900. And this is based on the NASA surface temperature series. And so an obvious question to ask about this is, how much of this is actually caused by us? How much of this is human caused versus just some sort of natural warming cycle, which you often hear people talk about as well. And obviously the warming itself, regardless of what's causing it, the warming itself is a real problem because there are real major impacts on people. So, heat kills. For example, the Russian heat wave in 2010 and the fires that resulted, we had over 55,000 deaths. And that's, kind of a mind-boggling number. And it's not that unusual either. The European heat wave that we had in 2003, that caused over 35,000 deaths. So heat kills. It also affects crop production, causes $15 billion of damage. Most of that was through impacts on crops. And then a publication, a climate publication, came out a year after this saying that this Russian heat wave was made 3 times more likely due to climate change. Now again, is that climate change due to humans, or is that natural? We know it's getting warmer, but really what's causing it, and how much is us versus some natural forces? Another thing that the heat, of course, does is it can melt the ice. It can melt the ice sheets, and this is something I spent a lot of my career focused on. And maybe a couple of weeks ago, many of you saw a headline like this in the media. So Greenland's ice sheet just lost 11 billion tons of ice in one day. And that's a pretty dramatic headline, and it's accompanied by a pretty equally dramatic figure. Now that's all glacier meltwater that you're seeing on the Greenland ice sheet, and there's so much of it that it's making rivers on top of the ice sheet. And of course, those rivers are flowing off the ice sheet and off into the ocean. So 11 billion tons of ice, it's a crazy big number, but what do you do with that number? I mean, how much ice does Greenland lose in a normal day in August? What about a normal day in August 400 years ago, right? We need some sort of context for this number to really make sense of it. And of course, this water, as I said, runs off into the ocean, and we worry about that because it contributes to sea level rise. And we know that in places like Miami Beach, high tide didn't used to cause flooding, and it does today. So this is a picture of what they call sunny day flooding. So it's just a normal high tide. No storm this day, but it's causing flooding. And this is costing billions of dollars in terms of the impacts to raise the level of the roads, raise the level of some of these buildings, the damage that's caused by even this minor flooding, not to mention just the sort of inconveniences to everyday life and commerce going on with this sort of flooding, and it's getting worse and worse. And then, of course, this is just a sunny day, and we know that when you combine this sort of sea level rise with a storm, that things get worse pretty quickly, like the nor'easter we had in Boston early last year. This was the #1 record flood level in Boston, beating out the famous, or maybe infamous, blizzard of '78. And this caused over $1 billion of losses in just a single storm, right? And of course, who could forget Hurricane Sandy? Just billions and billions of dollars in damage, not to mention lives lost and enormous numbers of lives just really negatively impacted. But again, you know, how much of these really catastrophic events, these hurricanes, these horrible storms, how much are these impacted by human activities? And how much of this is just, you know, these things happen. We have hurricanes. Bad things happen when you build on the coastlines. It's just natural things. How can we tease these apart? So that's what we're going to try and focus on here. How do we know what's natural versus what's from humans? And there's a few strategies that climatologists like me use in order to try and tease this apart. And we're going to focus on some of those strategies and then do some case studies. So first strategy is that we have to understand the natural cycles, right? If we want to tease apart the natural part, we need to know what's natural. What do these cycles look like? What causes them? How long is an individual cycle, right? And I think a lot of times you hear people talk about these natural cycles, and perhaps they don't have a great understanding of what those cycles might even be. Now, one of the problems is that a lot of these cycles are really long. So maybe a natural cycle might be thousands of years, and we only have really good climate data for maybe 100, 150 years. And so in order to deal with that, we have to create longer records of climate from things like ice cores. And we don't just use ice cores, we can use sediment cores that come from the bottom of the ocean or the bottom of a lake, or we can use tree rings. There's all sorts of different ways that we can get a sense of what climate was before the mid-1800s, going back thousands and thousands of years. But we're going to focus on ice cores today because that's what I focus on in my research. And then more recently, there's been a lot of work just to use the really latest generation outstanding climate models in order to create a simulation of what the climate would look like without humans. And then you can compare that to what the models show happens with human forcing in the simulation, or you could just compare it to what's actually happened, because we know in the real world, we have a combination of both. So you can compare what's actually happened to this imagined world without humans and try and tease out what is the impact of human activity really. And so we're going to use 3 case studies. We'll start off just by looking at that temperature record I just showed you, the actual signal of global warming since around 1900. And then we'll focus on Greenland and that 11 billion tons of ice. And what does that really mean? Give it some context and how much of that might be from humans. And then we'll look at extreme storms and extreme rainfall here in the Northeast US. I'm based here out of Hanover, New Hampshire, right smack in the middle of it. All right, so let's go back to this temperature record. And the first question we can ask, if we want to try and tease apart what's natural and what's human caused, is what could possibly affect temperature naturally? What might some of these natural cycles even be caused by? And so the first one that comes to mind as a climatologist is Earth's orbital cycles. And what I mean by that is, of course, we all know the Earth's orbiting around the sun, but our orbit is not the same all the time. Our orbit changes just a little bit through time. So for example, sometimes it's a little more circular and sometimes it becomes a little more elliptical. We know it's an elliptical orbit, but it becomes more elliptical. And that cycle takes about 100,000 years to go between more circular, more elliptical. And that changes the amount of radiation that hits Earth, and because the sun is really what drives our temperature here, that change in radiation will change temperature. Another thing that can change our temperature is actually the intensity of the sun itself. So not Earth's distance from the sun, that's that first one, the orbital cycles, but actually the strength of the sun itself. How much radiation is the sun putting off? Or how bright is the sun? And that actually changes through time. It changes most dramatically with sunspot cycles, but then there are much longer changes that instead of taking 11 years with the sunspot cycle can take decades or even centuries to change. Another big one that is probably on everyone's mind is changes in CO2. And we're not just talking about human changes in CO2. CO2 changes in the atmosphere quite naturally throughout geological history. And we know that CO2 really affects the temperature of this planet. If we had no CO2 in the atmosphere on Earth, the average temperature of the Earth would be -5 degrees Fahrenheit, -5. So we need CO2 in the atmosphere to have a habitable, comfortable planet. But the more CO2 we have, the hotter it gets. And so that can change naturally as well. And then two more things: volcanic eruptions can affect temperature, as well as things like El Nino. So these are ocean atmosphere patterns of change that we have on Earth that are just the sort of natural wiggles in the climate system. And so we'll talk a little bit about El Nino. And so one way to conceptualize this parsing apart of natural versus human is shown here in this schematic diagram. So we've got the observed warming, and that's the top curve there. And we can imagine, what if right now we're actually in a natural warming cycle? Well, then that means that the difference between that natural warming cycle and the observed warming is what's caused by humans. And if we're in a natural warming cycle, then that might mean that the human-caused warming is actually pretty small, and maybe something we don't have to worry all that much about, because eventually, that natural cycle will start cooling and the observed warming will go down. But what if instead we have that exact same observed warming? So that observed warming curve is the same in the top as it is in the bottom. But what if instead we're actually in a natural cooling cycle? And that means that human-caused warming has actually made up for that natural cooling and then created the observed warming. That means that the human-caused signature is actually quite large. And that would be a real concern, because it means that some point in the future, maybe we'll go into a natural warming cycle on top of the human-caused warming, and then things would even accelerate more. And so the real question is, which is it? What are we dealing with right now over the last 100 years? All right, so we're going to talk about some ice cores here, and so I thought I would give you a sense of how ice cores are collected, what they look like, how we analyze them, just real quickly here so we're all on the same page. So what I'm showing you is a picture on the right. Top right is a picture of South Pole. We're just a couple miles away from the actual South Pole Research Station, where we drilled an ice core back in 2015, 2016. And so what happens here at the South Pole and other glaciers, of course, is that the snow falls every year, and it creates sort of an annual layer of snow. You can imagine this sort of annual layer of snow. And then it doesn't melt over the summer. And so when more snow comes, next year's snow layer is on top of that, and that annual layer gets buried a little bit, and then the next year comes on top, and then the next year on top, and so on and so forth. And so each annual layer gets progressively deeper and deeper and deeper through time. And so as we drill down into the ice sheet to collect this ice core, we're actually drilling back through time. And each year going back in time can be seen in the ice core. And so the drill that we use for this core was actually a mile deep. So it took 2 field seasons to collect it, a total of about 6 months in the field. And this is a big scale industrial operation. To collect a mile of ice in a core is a lot of work. A team of about 15 people. You can see it's kind of an industrial sized drill. There's somebody on the right there is actually working on the drill piece at the moment. And when it comes up on the top left here, you can actually see the ice core inside the drill barrel. And so it has a diameter of about a coffee can. And when we take the core out of the core barrel, you've got the actual core, which is shown down the bottom right here. And so you have a beautiful, perfect cylinder of ice. And you can actually get a sense looking at it. You see the bands in the ice, the light bands, those are actually related to these annual snow layers I was talking about. And so in addition to the snow getting preserved, anything that lands on that glacier is also preserved with the snow. So for example, this dark band that you see in the bottom right here is actually volcanic ash from a big volcanic eruption from somewhere nearby in Antarctica. And so everything gets trapped. Any dust, any sea salt, any pollution that's in the atmosphere over the South Pole will get deposited on the glacier and preserved in the ice core along with the snow itself. And so what we do is we cut up these cores and we distribute it to scientists around the country and sometimes around the world. including to me here at Dartmouth. And I have an ice core chemistry analysis lab. And what we do is we take the ice and we cut it down into a little rectangular piece you can see in the top left. And then we melt it very carefully, very precisely, millimeter by millimeter. And when we melt the ice, we collect the melt water. In the bottom right, you can see some pumps and lots of tubing. That's taking the melt water and it's dumping it into very, very clean little bottles. And so every about centimeter, we're collecting another sample of meltwater that represents a little snapshot in time. And what I can do is I can analyze that water and measure how much dust is in it, how much sea salt in it, and I can tell you how the climate has varied in the past. We can even measure the weight of the water molecules themselves, the isotopes in the water, the hydrogen and oxygen isotopes, the actual weight of the molecule, and that will tell us the temperature at which that snow fell. So it can actually tell us the temperature of South Pole going back through time. All right, so let's look at what that looks like. Here I'm showing you the actual longest ice core record of temperature that we have on the planet. This is not from South Pole, this is from another site in Antarctica called Epica Dome C. And this is an enormous amount of time. This is 800,000 years of time. And whenever I show you a plot like this, the first thing you should ask yourself is, which way is time going? So in this plot, 800,000 years ago is on the left, and today is on the right. And just to give you a sense of, how much time 800,000 years is, remember that our species, Homo sapiens sapiens, only evolved and appeared on this planet 300,000 years ago. All right, so just a little before halfway on this plot. So this is an enormous amount of time. And what I'm plotting here is temperature. This is based on the weight of the water molecules. And I think, we often talk about the ice age. But what the ice cores show is that there wasn't just one ice age, but that there were many, many dozens of ice ages going back through time. And each ice age is separated from another one by a warm period like today. And so we can see today's warm period, which is a high time in temperature, and then the last ice age. And then about 120,000 years ago, we had the previous warm period and then the previous ice age, so on and so forth. So that these ice ages are paced about every 100,000 years going back through time. And what we know now is that what paces that is actually Earth's orbital cycles. It's those little wiggles in our orbit around the sun. But it's not just that. In fact, what it needs is CO2 as well. So now I'm plotting CO2 on top. And you may have seen a plot like this if you ever saw Al Gore's movie, right? What was that? Inconvenient Truth. He showed a plot like this, where you can see that the CO2 is really lock in step with the temperature. Whenever it's warm, there's lots of CO2 in the atmosphere. And whenever it's cold, there's not much CO2 in the atmosphere. And so what we understand actually happens is that it's the orbital cycles that cause the initial warming or cooling. So imagine that you're in the last ice age. It was the orbital cycles that started us to warm out of that ice age. And then once we warmed, it was really the CO2 that reinforced it and brought us fully out. And so what happens is you start warming from the orbital cycle, and that causes CO2 to go up. And then you warm more, and that causes more CO2 to go up. And then you warm more. And this is what we call a positive feedback or self-reinforcing cycle. And that will continue going on until the orbital cycle starts to cool it off again. And then that will cause CO2 to go down and cause further cooling. CO2 goes further down, further cooling. And so you can see it's a positive feedback regardless of whether you're warming or cooling. The CO2 will continue the trend of what the orbital forcing started. So that's what's pacing the ice ages. But this is a forcing that takes thousands and thousands of years, and we can understand this and really see it better if we zoom way in just to the last 10,000 years here. So again, 10,000 years ago is on the left, today is on the right. And so what I'm showing in red here is that solar intensity due to changes in Earth's orbit. And what you can see is that over the last 10,000 years, it's been decreasing. And what we know is that what that should do is cause Earth's temperature to go down. And what we see is that that is in fact what happened. In blue, over the last 5,000 years, we were on a long-term, multi-thousand-year cooling trend. In fact, this was the cooling trend that was going to take us into the next ice age. The next ice age in that pattern of ice ages we saw before. Until, of course, the late 1800s, the 20th century. the modern warming, this really abrupt warming that we can see here at the end, which clearly has nothing to do with this overall cooling that should be happening because of our orbital changes. Okay, so from an orbital perspective, we should actually be cooling now, and the modern warming is really quite unusual. What if we zoom back in on the last 100 or so years here and think about solar intensity, right, the strength of the sun? And so that's what I'm plotting here below in yellow. And you can clearly see the 11-year sunspot cycle. Those are the big wiggles in the solar intensity curve. But we can kind of smooth those out with a thicker line and trying to see how solar intensity has varied over longer time periods. And what you can see is that beginning in the late 1800s, solar intensity was actually going up. The sun was actually getting brighter until around 1960. And then since 1960, solar intensity has been going down. At the same time that our global temperature has been going through the roof, right? So solar intensity should, again, have been causing a cooling since around 1960. The warming that we saw from 1800 to 1960, some of that warming was caused by this small increase in solar intensity. Okay, so the solar intensity, natural change in solar intensity probably did contribute to the warming in the early part of this record up until about 1960. But since 1960, solar intensity is going the wrong way. In fact, the solar intensity that we're experiencing right now is the lowest that we have experienced in hundreds of years. Scientists at NASA believe, they hypothesize that we may be going into what they call a grand solar minimum. And the last time we had one of these was a few hundred years ago, and it was at a time that we called the Little Ice Age. Now, this is not one of those big ice ages we were just looking at that happen every 100,000 years. This was just a little ice age when, the Thames River would freeze over in winter and, mountain glaciers around the world grew bigger. And it was about a degree cooler than, say, 1950. All right, and instead of cooling off, in fact, temperature has been going up. So what can explain this? Well, here's CO2, right? And when you see this relationship, things start to become more clear, right? CO2 has been going up dramatically in step with temperature. But we saw in that previous ice core plot that CO2 goes up and down naturally. So is this just natural CO2? Well, let's go back here to this plot of CO2 versus temperature over long time periods. And we can see a couple things. One, the level of CO2 that we have right now, today, around 410 parts per million, is completely unprecedented for the whole length of the ice core. I mean, it's way off the chart, right? The highest it ever was naturally for the last 800,000 years was maybe 300. And we're up at 410 and climbing fast. All right, so in fact, the last time we were anywhere close to this was probably about 3 million years ago. So our species has never seen CO2 of these levels. The other thing that's remarkable about this modern CO2 rise is just how fast it is. So yes, CO2 was this high 3 million years ago, but it took millions of years to get there. And what we've seen in the modern rise of CO2 is that it's 200 times faster than even the fastest CO2 rise that we can see in this record, right? So some of these CO2 rises that you see coming out of the ice ages look really fast, but what's happening today is 200 times faster than those fastest natural rises in CO2. And we can see that if we really zoom in here just to the last 2,000 years. So 2,000 years ago is on the left, today is on the right. And now I'm not just plotting CO2 in red, but also two other greenhouse gases, methane and nitrous oxide. And we can see that CO2 is basically flat all the way up until the mid-1800s in the Industrial Revolution. Okay, so this is human CO2. And we can even get more complicated to prove that it's fossil fuel CO2 by looking again at the weight of the carbon molecules. I talked about the weight of the water molecules to get temperature. Well, we can look at the weight of the carbon molecules in the CO2 and prove that it comes from fossil fuels and not something like volcanoes or something. All right, so this human-caused CO2 is in step with this warming temperature. We can explain it with these other natural forces. We talked about a couple other things though, and people often ask me, well, if it's CO2, why does the temperature have all these wiggles? And it's not a nice smooth curve like CO2 is. Well, remember, there's a couple other things that affect temperature, like volcanic eruptions. So we know that when we have a big volcanic eruption, we actually cause cooling for a couple of years because all that ash and sulfur in the atmosphere, all the way up in the stratosphere, will actually reflect sunlight back into space. They act like tiny little mirrors, and that cools the planet off for a couple of years until that ash and sulfur clears up. And so what I'm showing here is what's happened to the amount of solar radiation after major volcanic eruptions like Agung, like Fuego, like El Chichon, and like Pinatubo. And so we can see with each one of these volcanic eruptions, solar radiation transmitted goes down. So there's less solar radiation reaching the planet, and we cool off a little bit. And so if we zoom in on that temperature record just since 1960 now, we can see that each one of these big eruptions is in fact associated with one of these cold little wiggles, right? Agung, Fuego, Chichon, and Pinatubo each had a year or two, in the case of Pinatubo, actually 3 years of cooling right after it. And then the last thing we talked about affecting temperature was El Nino. And of course, El Nino is these changes in the ocean surface temperature in the Pacific Ocean. And an El Nino event is a time when we have really unusually warm water right at the surface of the ocean in the Pacific, and that causes the whole planet to be a little warmer than normal. So El Nino events cause warming, but of course we also have La Nina, the other side, when we have unusually cold water right at the surface, and that actually causes a little bit of global cooling. So if we go back to this temperature record, we can still see those volcanic eruptions, but now we can see that pretty much every other down wiggle here is a La Nina event, and every other wiggle up in warming here is an El Nino event, including this really dramatic 2016 event that just shattered all the records, right? That was a combination of this overall steady trend in CO2, steady warming from human CO2, with a big El Nino whopper on top of it. So we can really start to understand this temperature record and understand just how much of this is from humans and how much is natural. The bottom line is that since 1960, this is all from humans. We should be getting cooler. And in fact, temperatures continue to skyrocket. July was just listed as the warmest month in Earth's recorded history. So I mentioned we can also use climate models to create a human-free world. And so that's what's shown in this figure. This is a figure from the IPCC report a couple iterations ago. And what it shows is that same temperature record in black. That's the record I've been showing you in red in previous ones, right? So you can see the global warming. And then two different model simulations. The one sort of shaded purple here is the climate model that has all forces, natural cycles, and human forcing in it. And you can see that that purple record, the purple climate model actually does a pretty good job of mimicking what has actually happened. But then if we run that same climate model with just the natural forces, just the natural cycles, and we pull out the humans, then you get the green. And as we kind of discussed, you can see that, sure, because of solar intensity increasing, we would have been slightly warming from around 1900 till the middle of the century, around 1950. But since 1960, we should be in an overall cooling trend. And in fact, we're dramatically warming. So here's the bottom line. The warming that we had up until then, until 1960, is some sort of combination of human forcing and natural warming, mostly from increased solar radiation. But since 1965, 1970, 75, if you want to be really conservative, that is all from humans. And it really strikes me how few people will come right out and just say that without sort of waffling or arm waving. We know this. This is in the IPCC report. This is rock solid science. It's not, some humans. It's not mostly humans. This is all humans since 1975. All right, so let's move on to Greenland. In this, this stirring headline and figure, what does it mean? How much of this is from us? How much ice does Greenland normally lose? How unusual is this? Well, in order to get those sort of questions, you have to actually go to Greenland yourself, because we only have observations, really good data from Greenland just for the last couple of decades. I mean, we can get pretty good data going back to 1979, because that's when we started having satellites. But I can't even get a good temperature record from Greenland before, from the ice sheet itself, before the late 90s. And even that has got big holes in it. So we actually have to go there, and that's what my team did in 2016 and 17. We spent 2 field seasons. Each one was 2 months long, and we were on a team of 5 of us on snowmobiles. And in 2016, we started at the bottom of this map at Die 2, and we spent 2 months going all the way up to Summit and collecting ice cores along the way. Each one of those red dots is a spot where we collected an ice core. And then in 2017, we went back and we flew into Summit, and we ended up making a sort of a clockwise circle starting at Summit and then going through 8, 9, 10, 11, and ending back at Summit, collecting another 9 ice cores. And so the question we were really trying to answer was just how unusual is this modern melt that we're seeing in Greenland, trying to put it into some longer context. And so this is what the logistics of this kind of operation looks like. Like I said, we're on snowmobiles. We have to have absolutely everything that we need for science, for living. I mean, we're living, sleeping, eating, everything on the ice sheet itself. We're almost entirely self-sufficient. We just had a couple of fuel caches that were put out ahead of time along the way. And so we're dragging sleds along with all of our equipment. And so we're making camp, and we're moving every few days, picking up camp and moving to a new one to collect another ice core every few days. And so this is kind of what our camps look like. We sleep in these orange tents in the foreground, and then you can see our kitchen tent is that bigger yellow tent in the background. And then, you know, you can see a pile of gear way in the background there, marked with big bamboo poles, and that's in case it snows. If things get buried, you got to know where to dig it back up. So that's why we have these long bamboo poles. And so again, what we were doing here is collecting ice cores, and these were relatively shallow. These were each only 100 feet long, 30 or so meters. And I mentioned that South Pole ice core was a mile long. And so whereas the South Pole is a big, big industrial operation, this is a pretty small scale operation. That's the actual ice core drill that my grad student Gabe is using right now. It's basically just a big old power drill attached to an ice core barrel, and we just do it all by hand. And then Karina on the left here is another grad student. She was weighing and measuring and logging the ice cores as they came up. And you can see our camp in the background there, our kitchen tent on the right, and that's our science tent on the left, and then the little white pyramid all the way over there is our bathroom, actually. So this is what it looks like from the air. We actually used a kite to take this picture to give you a sense of scale and sort of remoteness of where we are. And so on the left, you can see the trench where we collect the ice core and do all of our science, and we do that all upwind from our camp to make sure we're not contaminating our site. All right, so what we're looking for here is melt, right? We're trying to figure out how fast Greenland's melting. And so one of the things that's neat about meltwater is that when it forms on the surface, I want you to imagine that it's just a warm August day on the Greenland ice sheet. And so maybe for the warmest few hours of the afternoon, it gets above freezing, just above freezing. It's just say 35 degrees. You get a little bit of meltwater forming on the surface, and that meltwater will actually trickle down into the snow underneath it because it's denser than the snow underneath it. And then that snow is cold, and so it'll refreeze as a solid ice layer, right? So the way that the melt is preserved is as a solid refrozen layer of ice. And we can tell the difference between these melt layers from the so-called normal ice, because the normal ice has bubbles in it. It's individual snow grains that get compressed. But these ice layers from the melt are actually just pure ice layers like you would get, you know, if you were making ice in your freezer. And so we can see the normal ice here is sort of darkish, and the refrozen melt layers come out as these bright bands. And what you're doing here is you're looking down on an ice core that we've cut in half. And so what we can do is we can measure these refrozen melt layers in each part of the core going back through time and see how melt has changed through time. And so just for context, this is what the core looks like in, say, 2005, the part of the core that corresponds to 2005. And this is what the core would look like in the part that corresponds to 1866. You know, basically no melt back then. And so that's just 2 little snapshots. And so here's the actual full data set going back 400 years, 450 years. And so today, again, is on the right, 450 years ago is on the left. And what I'm plotting here is the amount of meltwater that we see in these cores in the form of these refrozen melt layers. And so you can see that there's a lot of variability, there's a lot of wiggles, and you can see some even longer term up and down wiggles. But what's clear is that the melt that we're seeing today, the modern melt, is really unprecedented for at least 450 years. Okay. The other thing that's interesting is that what we see is that the melting really just started in the mid-1990s. So another way to think about this is that Greenland is really just getting warmed up. It's not like Greenland has been melting quickly since the 1960s. We really didn't pass a critical threshold with Greenland where it really started melting fast until around 1995, 1996. So it's only been about 20 or so years that it's really been going. And so this is how this paper was covered in the Washington Post and Scientific American. It's melting faster than at any time in the last 400 years. And what we really think is that it's melting at the fastest time in at least 7,000 years. The last time it may have been this warm in the summertime here was when we came out of the last ice age, when that orbital, Earth's orbital forcing was still pretty high. Okay, it was high enough to pull us out of an ice age. And the Earth kind of overshot a little bit and was a little warmer, but then we've been on that 5,000-year cooling trend. And so this is the hottest it's been there in at least that amount of time. And of course, again, this water goes into the ocean, and we know that sea level is going up. So here's the actual data. It's not just anecdotal wet ankles in Miami Beach. This is the actual data of how global sea level has been going up as temperatures have warmed and as the glaciers and now the ice sheets have been melting. So we've seen about 7 or 8 inches of total sea level rise, global average, since 1900, but that rate is accelerating. So now it's rising at about 12.5 or 13 inches per century, and that acceleration is expected to continue throughout this century as we continue to warm. And so as we look to the future, so now I'm showing the actual, what's happened to sea level rise is in the little black squiggles, and then everything in the colored lines is future projections, depending on what we do in terms of CO2, how much CO2 we put into the atmosphere based on energy policy and so on. And so if we dramatically reduce CO2 emissions as a global community, then you get the blue curve. And if we continue on business as usual, you get the red curve, and green is obviously something in between. And so we're looking at somewhere of around 2 to 5 feet of sea level rise by the end of this century, by 2100. And so a couple things, take-home messages about this is that, first of all, there is a real difference here between the blue and the red. So our decisions about what we do with carbon, how much emissions we put out, do matter in terms of sea level rise. But even if we go dramatically on the CO2 reduction, the blue curve, which is arguably at this point unreasonable in terms of, maybe not unreasonable, but unlikely, I'll say, then disruptive sea level rise is going to happen regardless, and we need to prepare for it. And so what I would suggest is that this calls for a combination of mitigation, meaning do whatever we can to get CO2 down, and adaptation, meaning adapt to whatever sea level rise we can't avoid at this point. And it's an open question exactly how much sea level rise is already baked in, how much we can't avoid at this point. What's not shown in these colored lines is that there's huge uncertainties around them, huge, because the Earth has never done this experiment before. As I said before, yes, we've been this warm before deep in the past, but we've never warmed up this quickly before. And so we still just don't know how fast Greenland and Antarctica are going to melt, with how hard and how fast we're hitting it with this heat. But there are some reasons to be concerned that we're going to be more towards the red curve and that a lot of this might be baked in. And so I experienced one of these in person, actually, back in 2012. So we were doing research edge of Greenland in 2012 up in this northwest part called Thule. And if we zoom in here, what you're looking at is at an aerial view of a glacier on the left, and you can see a lake that is covered in lake ice here is circled. And we were camped down at the star in the bottom left here near another lake. And as we were flying in, we could see this lake here is the one that I was circled. It no longer has lake ice on it, but you can see that there's still a little bit there. And it kind of looks like it's overflowing. Well, overnight we were doing bear watch, and because we had polar bears around here, and we all heard the next morning the sound of like rushing water. We were all talking about it. And so a couple days later, as we were flying to our next camp, this is what that lake looked like. So the lake had catastrophically drained. catastrophically drained, probably in this time span of several hours, maybe a day, and flowed out underneath the ice sheet to the ocean. You can see the former level of this lake is that line against the hillside there where it goes from light brown to dark brown. So that same hillside is sort of shown over here on the right side. So this is the before, and that's the after. And so this is what it looks like. You can see there's this massive sort of crater where the ice sheet has dropped down because the water has put out the ice underneath it, and that water has gone out to sea. So this was a really dramatic, catastrophic event that is not captured by any of our current climate models, I'll tell you that. And it's a little hard to get scale here, so I actually have a video from the helicopter that gives you a better sense of scale of what this actually looks like. So here we're taking up from one camp, going up along the side of the ice sheet. You can see where some of the side, see these rivers we're working toward that collective. And these, under depression and then flow the lake surface. That's a little bit, and then as it pans out toward 10 or 20 years in Greenland, and we fully have our arms wrapped around just how quickly this is going to continue to happen in the future. But again, there's reason to be concerned. If we look at this curve, notice that these lines continue on past 2100. Hopefully, we're all around past 2100, and we're going to experience this, us not necessarily individually, but certainly as a species. And so the question is, where are these curves going beyond 2100? And again, there's reason for concern here. The last time that it was just 2 to 4 degrees warmer than today, sea level was 16 to 26 feet higher than it is today. Okay. Here, can you hear me? I think my headset just died. Ned, can you hear me?
Yes, we can hear you.
Okay, great. So I'm just going to drop the headset for now. So this is what the Earth looked like with just 2 to 4 degrees warming if we give the Earth enough time to actually equilibrate to that temperature. So I'm not saying that this is what the Earth is going to look like in 2200, but this is the path that we are on. Make no mistake that this is the path that we're on. And I can tell you that we do not know at what point this is unstoppable. We're actually spending millions and millions of dollars to try and figure out exactly where that point is. But this is what New York City looks like under 23 feet of higher sea level. This is the path we're on. And we don't know, maybe 2200 it looks like this, maybe 2300 under business as usual. We're not actually sure. That's the kind of scary part. But this is the path that we're on. All right, the last thing I want to talk about is extreme rainfall here in the Northeast US. And around here, that's really embodied personally by Hurricane Irene or Tropical Storm Irene by the time it got here in August 2011, where Vermont in particular was really walloped. Across the US, we had 47 deaths and over $13 billion in damage. And here in the Northeast, in New Hampshire in particular, we know that these kinds of things seem to be happening more frequently. We can see this in disaster spending, right? We're spending more and more money to deal with these floods. And if you look at the list of these events on the left, most of these are from flooding. That's what's causing most of our federal disaster spending here in New Hampshire. And then this figure came out in the National Climate Change Assessment Report back in 2014. And what it shows is that extreme storms, extreme rainfall has gone up by 71% in the Northeast just since 1958. And this was a pretty shocking figure for us to see. Having lived here for the last 42 years in the Northeast, I was a little bit skeptical, and I thought maybe it was cherry picked. And so we really dove in to try and understand what is happening here and why. And so here, instead of using ice cores, we're actually using weather station records. We're using the very best weather records we can find. They have to be over 95% complete to make our study. And each dot here represents the location of where a weather station was from. So when I say the Northeast, I mean everything from Maine down to West Virginia. And so if we look at how just the extreme rainfall, so that's rainfall that's more than, say, 2 inches in a single day. Now that's a lot of rain. That's the kind of rain that's going to cause some flash flooding usually. So if we just look at those events and we plot that through time, this is what we see. What we find is that really there was no trend from 1900 until 1995. That black trend line there, there's no trend whatsoever. But then in 1996, we didn't kind of steadily increase. We jumped 53%. And we've been, from 1996 to 2014, we've stayed in that elevated state. Okay, there's not a single year since then that's actually below the average from 1901 to 1995. So we jumped 53% in our extreme storms and rainfall, and we wanted to understand why, what was actually happening here. So what we did is we actually had to look at each one of these storms themselves. So we had 273 of these extreme storms over just the last 40 or so years, back to 1979. And what we had to do was categorize them. What was it? Was it a tropical cyclone? Was it a cold front in the summer that causes a thunderstorm? Or was it a nor'easter, an extratropical cyclone? And so we, or more specifically, my graduate student actually, went through 273 of these weather maps to categorize each one of these events to figure out what was happening. And most importantly, what happened in 1996 to cause this change. And so this is what we found and just published in the last couple of years, 2 different papers. That jump in 1996, we found that 48% of that jump, about half of that jump, was caused by hurricanes. About a quarter of it was caused by cold fronts, mostly in the summer, triggering really intense thunderstorms. And then about 15% was caused by nor'easters, these big extratropical cyclones. And so what's interesting about this is that it's not just one thing, right? It's not just hurricanes or just fronts or just nor'easters. It's actually all of them. All of the things that tend to give us flooding are all increasing since 96. And what's interesting about that too is that these are in different seasons. So the hurricanes are mostly in September and October, versus the nor'easters were mostly in February, March. And the fronts were mostly in June and July. So it's not just one season, it's not just one cause, we're seeing it across the board here. And so if we focus on the hurricanes and ask, well, what's causing that? What we found is that what's really changed since 96 is the ocean water temperature in the Atlantic. And so what the plot here is showing you is how ocean temperatures have changed since 96. And so everything that's in red means it's gotten warmer, and anything in blue, like below Hawaii there, it's gotten a little cooler. And so you can see that the whole Atlantic has gotten much warmer. And warm ocean water is like gasoline for a hurricane. This is what makes the hurricanes grow in strength, stay strong, and drop a lot of rainfall. And so what we found is that since 96, extreme hurricanes in the Northeast are 3.9 times more likely than they were before 96. And that the rainfall that happens during them are 4.2 times higher. So again, somewhere around 4 times more likely to have these extreme storms like Irene since 96 than we were before. And again, we think it's really this rapid warming in the Atlantic that's to attribute it to. And then what about these severe thunderstorms with cold fronts in the summer? Well, we tied that to the jet stream, actually. That's what usually causes these things, is in order to get a severe thunderstorm like that, you need a big wave in the jet stream. And what we found is that the jet stream has gotten much wavier since 1996, and that tends to give us these more extreme summer cold fronts and thunderstorms. And so, you know, I mentioned these climate models, right, creating a human-free simulation. Well, what's really exciting in climate science is that we can now do this on an event-by-event basis. It used to be that when you had something like an Irene, all we could say as a climate scientist and be, you know, really scientifically rigorous about it is say, this is consistent with what we would expect with climate change. But now we can do way better than that using climate models, because instead of just having one model, we can run the model dozens of times or hundreds of times and get really good statistics about what does the Earth look like with human forcing and what does it look like without. And then we can use those statistics to actually put more solid numbers on this. So for example, this is something that we just are working on now. It's a paper that hopefully will be accepted in the next couple of weeks. It's already been reviewed and revised, and we've resubmitted it for after revisions. And so what we focused on was this record rainfall in 2018, just last year, in Pennsylvania, Maryland, West Virginia, and New Jersey, sort of the southern part of our Northeast study area. And you may remember this massive flooding event that happened in Ellicott City, Maryland in May of last year, where this is what the downtown looked like, and then in the aftermath in the lower right. And so we were able to use these climate models to create a world without human forcing, to see how often do you get a year like this without human forcing versus how often do you get it with human forcing. And you can run that hundreds of times and change it a little bit each time to see what the statistics show. And so what we found is that human activities made it 1.5 times more likely to have an event like this. And then similarly, 2017, who could forget Hurricane Harvey down in Houston and these horrible images that we were seeing? Well, lots of other research groups are starting to use these techniques. And again, this is like just in the last couple of years that we can do this. And so this paper found out that Hurricane Harvey was 3 times more likely because of human activities, and that those human activities caused 15 to 20% more rain than we would have had without human activities. All right, so here's my take-home messages. Warming since 1975, and probably more like 1965, is all from human activities. We should have zero ambiguity about that. We should be in a natural cooling cycle right now, based on both orbital cycling and based on the intensity of the sun. But yet we've had record temperatures after record temperatures. Human activities are in fact causing the ice sheets to melt rapidly and for sea level to rise, and that is accelerating. And I do think that it is an open question at what point this really catastrophic sea level rise, let's say 20+ feet, at some point in the future. No, it's not in our lifetimes. It's not even in our children's lifetimes that we can see this. That's not geologically possible. But what does it mean to you if in our lifetimes, maybe in this decade, we are locking that future in and there's nothing that future generations can do to stop it? That's a really interesting moral dilemma. And scientifically, we don't know where that point is yet, but more and more evidence is showing that it's closer than we hope. And that human activities are already causing storms and extreme rainfall to become more frequent. And so, Ned mentioned that I try and do things beyond just my hardcore climate research here at the university, but I'm trying to figure out what I can do to try and help the situation. And so I'm part of a group along with Michael Simpson, our sort of co-host here at Antioch, of something called the Upper Valley Adaptation Work Group. And so our mission is to build climate resilient communities here in the Upper Valley of New Hampshire and Vermont. And so one thing that we're starting just in a couple of months in October, for the first time ever, we're doing what we call a Leadership Academy, where we're going to bring in about 25 community members who are interested in becoming leaders and catalysts for action on climate change, not just talking about it, not just giving presentations, which I do a lot, but actually doing something about it, right? Acting to lower our CO2 emissions or to make our communities more prepared for what's coming. So with that, I'll put my take-home messages back up here and be happy to take any questions.
Thanks, Eric. Really appreciate that. And we do have some questions. One person was asking you to explain in a bit more detail the idea of isotopes and molecular weight, and specifically why does a water molecule weigh something different when the temperature changes?
What a great question. So that is, that's at least a whole lecture right there in itself, but I'll try and distill it down as quickly as I can. So the way to think about it is that the water in the atmosphere generally comes from the subtropics, from around 30 degrees south or 30 degrees north, depending on your hemisphere, right? And so the temperature around there is pretty stable. And so if the temperature of, let's say where moisture is coming from 30 degrees south in the South Atlantic, if it's going down to Antarctica, as the temperature cools, it causes that moisture to condense. And we know that as water condenses out of the atmosphere, the heavier isotopes of oxygen, say, the oxygen 18, will condense out first, preferentially. And so what that means is that the vapor that's left in the atmosphere, as you progressively rain out that heavy oxygen isotope, that oxygen 18, the stuff that's left behind is progressively isotopically lighter and lighter and lighter and lighter. Now, if the temperature at 30 degrees is not changing very much and the temperature in Antarctica cools off a lot, that means that it's going to rain out more on the way to Antarctica before it gets there. And so that when that vapor finally does get there, it has a lighter isotopic signature. And then if it's warmer, then it's going to rain out less on its way to Antarctica from the moisture source. And so the isotope, the snow that falls on Antarctica is going to be isotopically a little heavier. So it's to do with how much of that heavy isotope are you raining out on the way to your ice core site. And that is a temperature-driven relationship.
So another core question is, how can you age a sample from an ice core?
So what's great about nearly all ice cores these days is that we can actually count individual layers back through time, just like you could count rings in a tree. And that's because a lot of things that happen in the polar regions are really different in summer versus winter. So obviously the temperature is really different, but even the winds are different. It's much stormier in the winter. And so, for example, if we look at our record of how much sea salt is coming up from the ocean, more sea salt comes from the ocean and lands on the glacier when it's stormier in the winter. And when it's calm in the summer, there's less. And so you can actually see an annual cycle in the amount of sea salt in the core. And so when we do these analyses in my lab, we're taking a sample, like I said, every centimeter. And so what that means is that we can usually get about 10 or 12 samples in a whole year at the South Pole. And so we can see these cycles, and we literally sit down, and it's incredibly time consuming and tedious, but we can count these cycles one by one back through time. And then to make sure that we're right, we can compare that to big volcanic eruptions, which show up as those big dust spikes and big sulfur spikes in the core. And a lot of those volcanic eruptions are known precisely what year they happened, either because they're in the historical record or because they've been dated through some other geological technique. And so we come up with our own time scale, and then we check it against the volcanoes to make sure that we're right on. But it's really remarkable how we can count each year back through time, just like the rings on a tree.
Cool. So what are some of the natural sources and causes for those sources to increase the flux of carbon dioxide emissions that come along with warming?
Fantastic question. So the best analogy for this is a bottle of soda. So imagine you take a bottle of soda out of the refrigerator. You unscrew the cap, and the first thing you hear is, right? That's CO2 coming out of the soda as you depressurize it. So now you allow it to fully depressure as you drink a little bit. You put the cap back on, and then you put the soda down on the desk, and you allow it to warm up a little bit. And then you take the cap off again in a few minutes. What do you hear again? Maybe not as big as the first one, but you hear a little more CO2 coming out. And that's because soda, and it's the same for the oceans, can hold more CO2 in the dissolved phase. It can have more CO2 dissolved in it when it's colder. And so let's think about those ice age cycles. The ocean has got lots and lots and lots of CO2 dissolved in it. And so the orbital cycles cause the oceans to warm up a little bit, and then CO2 comes out of the oceans and goes into the atmosphere. And it's the CO2 in the atmosphere that we care about, because it's only the CO2 in the atmosphere that causes it to warm or to cool. So as the oceans warm up, they release CO2 and cause it to warm further, which causes more CO2 to come out of the oceans and cause it to warm further, and so on. And if the oceans start cooling down for some other reason, it means that they can absorb more CO2 out of the atmosphere, and that will cause further cooling. Now, this is super important because right now, CO2 is dramatically going up mostly because of fossil fuels, right? That's us taking carbon out of the ground, burning it, putting the CO2 in the atmosphere. What the ice core record shows us is that naturally, as we warm, we're going to have more CO2 come out of the oceans, right? So these natural processes are actually going to work against us and make it warmer and warmer and warmer. So we're going to have to fight those natural tendencies of the ocean to put more CO2 up there by putting way, way, way less of our own human CO2 up there. Does that make sense?
It does. And a companion question came in about land-based greenhouse gases. Specifically, what will be the effect from thawing permafrost and releasing methane into the atmosphere?
So there's a lot of concern about that. And so the quick answer is that that permafrost has a lot of carbon stored in it in the form mostly of methane, that as that permafrost thaws, that methane can get released in the gas form and put back into the atmosphere. And methane is a very powerful greenhouse gas. People talk about it being more powerful than CO2. I don't like thinking about it that way because CO2 really is way bigger of a problem than the methane. For one, methane comes out of the atmosphere within a few years. CO2 stays up there for centuries. So once the CO2 goes up, it's really hard to get it out unless you're like actively filtering it out of the atmosphere with technology that we don't really have yet. So the long answer though is that we don't actually know how big of an impact that will have. There's some evidence that as the permafrost thaws, so do the critters who live there. And some of those critters actually consume methane. And so it's unclear exactly how much of a huge deal this is. It has the potential to be a big deal. One thing that makes me feel a little bit better is that when we look in the past in the geological record, we don't see huge plumes of methane showing up in the past when it was a little warmer than today. Like, you know, I showed 125,000 years ago when sea level was 23 feet higher because it was a little warmer. We don't see lots and lots of methane in the atmosphere in the ice cores at that point. So that gives me a little bit of hope that this isn't going to be a catastrophic thing, but it is something of concern, and it's something that a lot of people are really actively researching right now.
Interesting. Someone was asking, David was asking, how much of relative sea level rise is due to land sinking? And I think he also is wondering about land rising after glacial retreat. He didn't say that, but he asked about relative sea level rise. So maybe you could speak to relative sea level rise.
Yeah, so great question. It really depends where you are, right? And so where we are in, say, the United States East Coast from North Carolina up to Boston, that whole coastline is sinking, partly because we're sucking out so much groundwater out of the ground, and partly because of the ground is sinking after the last ice age still. And so here is some math that you guys, if you can still see my slides here. So if you imagine a very low sea level rise scenario of say 20 inches of global sea level rise, in this part of the mid-Atlantic coast, you might expect an extra foot on top of that. Now, on top of those two things, we also have changes in things like the Gulf Stream, which is the big warm ocean current just offshore the East Coast. And that will also slow down with global warming. And when it slows down, it actually causes further sea level rise. So another 8 inches might just be from the slowing down of the Gulf Stream. So the point is that you do have to be very careful about these global sea level rise numbers, because you could have a global sea level rise of 20 inches, and you could have a local sea level rise in Norfolk of 40 inches, twice the global average, right? So in some places, these land changes, these rising or sinking of the land can be hugely important. I mean, you look down in New Orleans, the land is sinking dramatically, and so sea level rise is much faster there. You can look up in Scandinavia, and in those places, the land is rising. And so local sea level, the sea level right there on the Scandinavian coastline, is actually going down. So yes, you always have to be careful with these global sea level curves. You got to know what the land is doing locally. And unfortunately for us in the United States, the East Coast of the US, where we have this big population center, economic center, government center of DC all the way up through Boston, it's sinking. And so whatever global sea level rise we see, we're going to expect more than that along that coastline.
Well, thank you. We have several questions we're not going to have time to get to. John Callahan, Leslie Kurian, Lindsay Webb, Arjita Rai, Emily Sheridan, Jane Hines, Colleen Sanders. We're going to get to your questions tomorrow. Eric and I are going to have a follow-up conversation in which we take your questions and we have a conversation where we round out this presentation. And at that point, once we have that conversation tomorrow, we will follow up with you by posting this link to this final Q&A session along with this recording of this webinar, and you will get notification of that. You can check the website when you have a moment. So I want to thank Eric for your time today and for the conversation tomorrow in advance. Also, we should thank the sponsors of this webinar series, Town Creek Foundation and the High Meadows Fund, who've made it possible for Antioch and NOAA to collaborate on this webinar series. So thanks for that. And Abigail, if you have any closing words, we can hear from you before we sign off.
Thanks so much, Ned, and thank you so much, Eric, for today's presentation. This was really compelling, and if it doesn't cause all of us to want to take action immediately, I don't know what would. So I just want to thank everybody for joining today's broadcast. As I said at the beginning, this is the first in our 6th year of this webinar series, and we'll look forward, told you earlier, and we look forward.
All right, and with that, we're going to end the broadcast. Thanks, everyone, and we'll see you next time.